Hey guys, sorry again for canceling class. Was not feeling too great. Um, but I hope you guys were able to watch Charlie's supplemental video. Please do if you have not done that so far, because I am going to assume that you have, and I'm going to move on to how to deal with the falling regime of the walking arm trebuchet. And of course, if you have any questions regarding the general process of what Charlie went over, shoot me an email. I'd be happy to talk about it. All right, so I hope that you can see my screen of my OneNote now. Anyways, let's see. Cool. So basically what we're going to do is we're going to be using the vector loop to derive the equations for kinematics and the kinetics of the falling regime. Within the falling regime, basically like all three links rotate at the same omega because they're all rotating about point D. So we're going to use our vector loop equations to encapsulate how we want to describe this rotation and how we want to find our state vector here. So basically, our state vector is going to be the three angular positions of the three lengths. So theta 1, theta 2, and theta 3. And thus within these vector loop equations, we're going to be dealing with the state vector derivative, which is theta 1 dot, theta 2 dot, and theta 3 dot. And then the state vector double derivative, which is theta 1 double dot, theta 2 double dot, and theta 3 double dot. Okay. So now the first thing we want to do is let's look at our vector loops. So we have three vector loops. Now, give me just a second to snip this and bring it over. So this is going to be your first vector loop. And based on this, we want to form equations for the kinematics. So basically, you're going to solve like for position, velocity, and acceleration using vector loop method you learned in lab 5. But this time, since our state vector is only a 3x1, so basically, yeah, you're gonna do that for that vector. That's how the first vector loop is. This is a loop 1, which is all links. And then you have loop 2, or which is going to be this here. Because you're just concerned, like basically what each of the loops do is they have relations from like loops are relations from pivot point D to center of mass of each link. So I believe that link 1 is defined as AC, link 2 is defined as BD, and link 3 is defined as DE. So loop 1 is going to link 1, loop 2 is going to link 2, and loop 3 is going to link 3. So I'll show you how you should, and the reason why I'm giving you these vector loops is we want consistency. And this is really going to be the proper way, even though you could draw them. I mean, loops 2 and 3 are going to be very straightforward. But loop 1, we want consistency across all the students. All right, so there you have it. You have all 3 of your loops. So D to center mass of link 3. D to center mass of link 2. D to center mass of link 1. Actually, ignore this. All links are applicable for all loops. Okay, so now that we have this, how do we interpret the 3 loops? So how do we combine the equations from the 3 loops all together? First of all, link 1, which is loop 1, you're going to get expressions for x dot 1, y dot 1, x double dot 1, and y double dot 1, which are corresponding to the velocities and acceleration. And then this one we have x dot 2, y dot 2, x double dot 2, y double dot 2, and of course x double dot x dot 3, y dot 3, x double dot 3, y double dot 3. And of course you would have like the x3, y3, x2, y2, x1, y1. So yeah, those are your on the left hand side, but we have to combine all 6 of those unknowns with our state vectors. So what we're going to do is called augmenting the state vector, which means we're adding those terms. We're adding the state vector to our vector with our position. So what this is called chi. So for velocity, you're going to have chi dot equals, I'll try to make this distinguishable, a x dot. So when I draw a x like this, it's called chi. And then this is the derivative of the state vector. So that chi is going to have theta 1 dot, theta 2 dot, theta 3 dot. So you're going to put your state variables in there first, but we have to augment it, meaning increase the size of the matrix to have x dot 1, y dot 1, x dot 2, y dot 2, x dot 3, y dot 3. And that's going to be chi dot. And then you're going to have your A matrix, which is going to be a 3x9, sorry, a 9x3 matrix, because this is a 9x1. So this is going to be a 9x3, and then you have your derivative of the state vector. So that's theta 1 dot theta 2 dot, and theta 3 dot. So 3 by 1. So you're going to end up getting a 9 by 1 for your x or chi dot. So what you're going to want to do is like isolate the like x1 x or like the x dot and y dot terms on the left hand side, and like all the theta dot 1, theta dot 2, theta dot 3 on the right hand side. Okay, so that takes care of velocity. But now, how do we deal with acceleration? So acceleration is similar process, except the equation is going to be chi double dot equals a. The A matrix stays the same. X double dot, double derivative of the state vector, plus b leftover terms. So with this, it's going to be the same vector size. This is a 9 by 1. This is going to be a 9 by 3 times a 3 by 1, and the B matrix is going to be a 9 by 1. So you want to isolate x double dot, y double dot terms on left hand side and put terms with theta double dot 1, theta double dot 2, theta double dot 3, and theta dot 1, theta dot 2 squareds. Those are going to be squareds. Theta dot 3 squared on right hand side. Okay. So that just about covers the kinematics of the following regime for using the vector loops. It's really important just to follow vector loop convention. Like, don't try to change the signs. Follow the rules that I presented to you in the first week we introduced it. Now, we're going to go over kinetics. So, because we have center of masses at each of the links, so we have gravity forces that are acting at each of the center of masses. I'm going with kinetics. We actually have to do a free body diagram and a kinetic diagram. So this is like the Newton-Euler method. So basically what we do, since D is a pivot point, right? D as in dog is a pivot. So we sum moments about D. It also, we can avoid the reaction forces at D because we do that, which is really helpful. So from this, we have the sum of the moments of D on the FBD side. So that's the left-hand side, is equal to just R1 cross F1. In F1, I'm calling the like M1G, the gravity. R2 cross F2 plus R3 cross F3. R1 is the position from D to the center of mass of link 1, and so on and so forth for the other ones. Okay. Now, on the kinetic diagram side, we have some of the moments about D on the KD. So we're going to have our inertia terms. So I bar 1 A plus the angular momentum terms. So on and so forth for the other links. So what we're going to end up having is some of the moments of a D K hat direction is I bar 1 theta double dot 1 plus whatever you derive for R1 cross M1 times X double dot 1 I hat plus Y double dot 1 J hat. And you're like going to be substituting those in, and then and so on. And then you have certain constraints because all three links are rotating at the same, all three links are rotating together as a rigid body. So that means that theta double dot 1 is equal to theta double dot 2 and theta double dot. Did I say constant omega in the beginning? Because that's not true. Sorry. Theta double dot 1 is equal to theta double dot 3. Okay, so now the left-hand side of the FBD KD, that's going to be encapsulated within the vector F. Okay, and this F is going to be equal to M times X double dot, or chi double dot, I'm sorry. So this is going to be like the right-hand side stuff. So KD terms. So what we want to do is chi double dot. We want to actually expand that out to include X double dot. So F is equal to M times A X double dot plus B. Thus F is equal to M times A X double dot plus B X double dot, or plus B plus N times B. So MAX double dot is equal to F minus MB. Then X double dot is equal to MA inverse. This is just basic linear algebra. Okay, so we did all that. We did everything just to get this. This is how kinetics affects your angular accelerations of all three links, which is your state vector double derivative. That's how you simulate the system with kinetics. I have posted on Canvas a PDF of all of the correct matrices for velocity and acceleration, as well as the F matrix and the M matrix. So I suggest that as you're working these through, to double check with what I have. I thank you for watching this video. I'm sorry that I went a little long, and I hope to see you guys soon in office hours. And please ask me questions via email. Please read the assignment in the lab manual thoroughly, As well, it's definitely watch Charlie's supplemental video before you watch this. I guess if you've gotten this far, you've already watched this, but yeah. Anyways, thank you guys. Have a great night.